Welcome everybody to our special Fellows Lecture featuring our very special guest Matthew Bales, who's going to talk to him about his work about Einstein's gravity. So my name is Professor Karen Hapgood. I'm the Deputy Vice Chancellor here at Swinburne University of Technology, and it's my pleasure to welcome you here today. I'd like to start by acknowledgement of country. So respectfully acknowledge the Wurundjeri people of the Kulin Nations, the traditional owners of the land on which Swinburne's Australian campuses are located in Melbourne, and pay our respects to their elders past, present and emerging. And for those of you joining online, I'd also like to pay respects to the elders of wherever you are located watching this today. We're honoured to recognise our connection to Wurundjeri country, the history, culture and spirituality, and strive to ensure that we operate in a manner that respects and honours the elders and the ancestors of these lands. I also respectfully acknowledge Swinburne's Aboriginal and Torres Strait Islander staff, students, partners, alumni and visitors. I'd also like to respect all the lands and to also note that our Aboriginal and Torres Strait Islanders were our very first astronomers in this country. They have a long history of being interested in the greater stars in the universe, and so there's also a long knowledge tradition in the Indigenous cultures in Australia. So today, the purpose of this lecture is that Professor Mr. Matthew Bales has recently been elected to a Fellow of the Australian Academy of Science. This is the biggest, most prestigious body in Australian science. It's very prestigious. It's a lifetime of achievement or significant achievements over a career, which makes Matthew very uncomfortable as he edges towards the door as I'm saying this. But it is a thing that it requires quite a process and there's quite a distinguished process about acknowledging the leading scientific minds in the country as recognised by the fellow system. There are not very many. I think we've worked out there are 2 fellows, including Matthew now at Swinburne. There might be more. If I've got them wrong, let me know. But this is quite an unusual offer. It's a very big honour and unusual distinction, and that's why we have the and so I had a great idea to have a special Fellows lecture, and we hope that we'll have one annually from now on. But in the meantime, we have a really excellent day today, and I hope you really enjoyed it. I'm going to hand over to Enzo to do the introduction. So, Enzo.
Thanks, Karen. For those who don't know me, I'm Enzo Palumbo. I'm the Associate Dean Research for the School, what are we called now? School of Science, Computing, Engineering Technologies. And it's my pleasure to welcome Matthew to this special event. I'll read a few words from the press release that came about when Matthew was appointed to the Academy. Matthew Bales is a pioneering astrophysicist and has been recognised for his outstanding contributions to science by his election to as a Fellow of the Australian Academy of Science. Matthew specialised in the study of pulsars, fast radio bursts and gravitation, and has made major contributions in establishing Australia's high international profile in these areas. He's played a pivotal role in the development of a new branch of astrophysics, fast radio bursts, developing pioneering instrumentation and software that led to Australia's early dominance in the field. And he has put Swinburne at the cutting edge of astrophysics. He joined Swinburne in 1998. Is that correct? Yep. And established Swinburne's Centre for Astrophysics and Supercomputing and serves as the director for the first 12 years. And I remember I joined a few years after Matthew, and I thought, we do astronomy at Swinburne. Who built the telescopes? Where's the observatory? I thought, that's not a very unusual place to put an observatory. Then I realised it's all done by special computers and other clever tools. And I remember you guys used to occupy almost a whole floor on the top of the AS building, had a wonderful big tea room up there. So this special people, they got a whole tea room to themselves. That was slowly taken away, wasn't it, over time? But anyway, it did recognise that was the vision of our then Vice Chancellor, Ian Wallace, to bring astrophysics into the university, and it's become pretty much one of our dominant fields of research. Matthew has graduated, or the Centre has graduated over 100 PhDs, and also pioneered online education at Swinburne through the Astronomy Online program. In 2016, Matthew was appointed as Director of the Australian Research Council Centre for Excellence for Gravitational Wave Discovery, or known as OzGRav. And just, I mean, I know we don't always like to mention numbers and metrics, but in this case, I think it's very important to recognise Matthew's contributions. And a quick Google Scholar search, Matthew has 639 documents recorded with over 36,000 citations and an H index of 91, which those people know what that means. It's incredible. In the last 5 years, he's attracted over $50 million of research funding and has also had 24 HDR students complete during his time at Swinburne. So, Matthew, without further ado, it's my pleasure to give you the floor. And today's lecture is The Quest to Understand Einstein's Gravity. So, thank you, Matthew.
Yeah, I hope you can all hear me. Thanks very much, both Karen and Enzo. And I'm specifically touched to see so many people from outside of astronomy at this lecture. I've always felt part of the entire Swinburne community and been very grateful to the hard work that many of you do in order to deliver courses to full fee-paying overseas students to help fund my toys. Just at the moment, I'm the director of OzGRav, but this journey started a long time ago. And it really started with my own fascination for sort of how the universe works. And so when I was coming up with a title, I thought this was really about the quest to understand Einstein's gravity. And just to echo Karen's thoughts about the Wurundjeri people of the Kulin Nation, so I'd also like to perform my own acknowledgement of country and acknowledge that the Wurundjeri people of the Kulin Nation are the traditional owners of the land on which we are present today. I actually have my own sort of minor connection to the Aboriginal people. The gentleman in the bottom left-hand corner is my second cousin, the late Billy Bales, who passed away just over 10 years ago. And I found it very interesting that I actually had no idea this guy existed for most of my life. It was only my brother who got interested in family trees and started raiding telephone books for Baleses, and we're quite rare. And he came across Billy Bales and made connection and found out he was actually my brother's second cousin. But many years ago when Billy was born, it wasn't the done thing to talk about your Aboriginal cousins. And we actually share a great-grandfather. And I think it's sad that we were just quite happy to effectively have offspring with our original co-inhabitants of northern South Australia, where my grandfather tried to start a goat station. Unfortunately, a 7-year drought ended that. So I do think it's, if you compare the opportunities I had to what Billy had, it's really quite moving. So this is me in Alice Springs, near our sort of pastoral home. We'd actually moved to Adelaide in between after we lost the Bales family fortune in the desert. But Billy was actually narrowly avoided becoming part of the stolen generation. Some of his brothers and sisters didn't avoid that fate. And he lived near the old cottage that my grandfather and his brothers had established at Bloods Creek Station. So I was actually born in 1963, and Queen Elizabeth II was visiting Alice Springs at the time. And you'll see why that's relevant a little bit later on. So she actually departed on the same day I was born by air. They used to type things up, and my father was a leading public servant in Alice Springs at the time, and it was his job to host the Queen, and so he wasn't present for my birth, but men didn't really do that in those days anyway. And so we lived in Alice Springs, and on the same day I was born, this interesting publication appeared in Nature, 3C273, a star-like object with large redshift. And this was actually the discovery of a whole new class of object. It was the discovery of supermassive black holes in the universe, and the fact that they were incredibly luminous and people couldn't explain their luminosity without invoking Einstein's theory. So it's kind of curious that I was born on this day and that the Queen was visiting and that we lived in Alice Springs. And you don't meet many other Alice Springs scientists. So I had an interesting fascination in how the universe worked. And my parents weren't super educated. I think their mum left school, I think, in year 11, and my father around about the same time. So they hadn't been to university. And I used to ask them all sorts of questions about how the universe worked, and they couldn't really answer them. And my father was not a very good role model for how to cross roads. And so I used to have to walk to school and cross something called Swinburne Road in Adelaide. And it was this dual carriageway road. And rather than use the pedestrian crossing, my father had taught me that you didn't have to do that if you were going to the football, which he and my brother used to do. And he would, rather than go down to the crossing, he would cross the street wherever he felt like it. And he didn't realise that his son, who was 5 years old and used to walk to school, would invoke this when nobody was looking. And I used to cross this road, and I remember looking at an oncoming car and wondering why it was I could see it. And maybe sometimes you couldn't see it, and maybe I would be killed. And so I asked my father and mother, why can I see the cars? And they didn't really give me a very satisfactory explanation. And so I just had an interest in science and how the universe worked and staying alive. And I did manage to cross Swinburne Road for 7 years without fatality, but it probably wasn't a great idea. So anyway, I went to a state school, and I think this is particularly pertinent to Swinburne because I think we do draw a lot of our students from people with similar schooling to myself. It wasn't a particularly great school, but it wasn't a terrible school. I mean, I think in Australia these days we try and point out how disadvantaged we are, almost as a matter of course. I wasn't terribly disadvantaged. It wasn't a bad school, it wasn't a great school. It certainly didn't want to reward academic excellence. It was quite progressive in that way, that no academic merit should ever be given to anybody. So although I used to have certificates for being the school chess champion or being in the debating team, I didn't ever get any awards for academic prowess. And it was interesting that the school's academic performance wasn't actually that great. Fortunately, one of my best friend's father was a physicist, and he could answer questions for me. And I really enjoyed physics, but my father thought it would be terrible if I was to become a scientist. He was actually a public servant, and he used to, one of his roles was to interview people for the public service. And he often had unemployed PhDs coming to them out of desperation, wanting a job. And he thought if you did a PhD in science, this was your fate. He was rather disappointed when I didn't want to do medicine, because he thought if you had an ATAR or whatever it was called back then, capable of getting into medicine, you should do it. And so he compromised on electrical engineering. And it wasn't long before I started attending physics lectures, and I had a Professor McCoy, who was a wonderfully exciting lecturer and talked all about the personalities behind physics. And I really fell in love with physics and tried to inform my father that I was going to change to a science degree, and he wouldn't have a bar of it. And I was pretty stubborn back then. Maybe I still am, I don't know. And so the next day I went in and enrolled in physics and left engineering. And I told him about it, and he sort of didn't really speak to me for about the next 10 years, which was kind of unfortunate. But luckily his sister, who was my spinster auntie, died and left some of her fortune to me. And so I wasn't really financially dependent on him. And I was also very lucky to be in an era where HEX hadn't been invented yet and education was free. So I went to Adelaide Uni and I did physics there and mathematical physics with a guy called Peter Zekaros, who was the son of a famous relativist. And I got into an argument with Peter about why I wanted to do an honours project on astrophysics, and he was the only person in the department who could possibly supervise it. and he was trying to talk me out of it. But he ended up giving me a paper on something called the binary pulsar, which was two neutron stars that went around each other every 7 3/4 hours. And he couldn't understand how you could possibly get two neutron stars orbiting each other. A neutron star is the product of a supernova explosion when a really massive star blows up, and it leaves behind the central core of the star, which is made entirely of neutrons. 1 teaspoon weighs as much as all of humanity. And they're super dense, but when they blow up, or when the star blows up, how could the binary remain bound? So my honours project was on this object. It's a picture of me near the time. So this is the binary pulsar's most famous graph, and it actually won the person who presented it the Nobel Prize in Physics. And what it shows is against time when it was discovered in 1974 to around about 1993, I think it was. They measured when the two neutron stars got to their closest point of orbit, and they saw that they were getting there faster and faster. And this was consistent with the emission of gravitational waves, which is a mysterious form of radiation postulated by Einstein. And this was about the only system in the entire universe that we knew of where you could test this theory of relativity to see if these things called gravitational waves existed. So little did I know it, back in 1984, being handed this paper about gravitational waves actually led me to, a few decades later, being the director of the ARC Centre of Excellence for Gravitational Wave Discovery. And the thing that blew me away about this was that the orbit, these systems are about 20,000 light years away. They were orbiting every 7 3/4 hours, and the orbit was shrinking by 3 millimeters in orbit, and they could measure it. And not only could they measure it, they could win a Nobel Prize for it. And the gentleman who won the Nobel Prize, Joe Taylor, actually became a friend of mine, and he marked my PhD thesis. He taught me a lot about how to get a really good group culture in your group. And one of the things he did was when I visited him in Princeton, he personally drove out to the train station to pick me up. And he actually took us to his house. I think my wife was with me. And we stayed in his house, even though he didn't really know me. And he threw a party, and all of his group came. And it was just taught me a thing about how to get a very good group ethos. And if you look through all of his students, a lot of them went on to these amazing careers in science. And some of them are my competitors now, but also friends. So here is a pulsar. They weigh about 500,000 times as much as the Earth. They're only 20 kilometers in diameter, and they have a very high magnetic field, which generates an enormous potential drop across their polar cap, and they act as a particle accelerator. And they have something like 10 to the 12 to 10 to the 15 volts above the polar cap, and that accelerates charged particles into the magnetosphere, and something magic happens, and one of the byproducts of this acceleration in the changing magnetic field is synchrotron radiation, and that gives rise to a radio beam which sweeps throughout the universe. And if you're lucky enough to point a radio telescope at these objects, every time they rotate, you get a pulse. And remarkably, the first one of these objects rotated about once a second or so, but we now know of these objects that can spin 700 times a second. So this neutron star, 20 kilometers in diameter, is rotating 700 times a second and giving off a pulse just over every millisecond. So how could you possibly form such a thing? Well, you're all familiar with the Earth. We live on it. The Earth is about 40,000 kilometres in circumference. In fact, that's how the metre was originally defined. There was going to be 10 million metres from the North Pole to the equator. But there are plenty of objects in the universe that are bigger. So this is the planet Jupiter, which you can see with your eye. And this is the Sun. So the Sun is over 1 million times the volume of the Earth. It weighs about 300,000 times as much as the Earth. And the densities inside the sun are so great that we actually have a very high temperature and nuclear reactions, and we're converting hydrogen to helium and helium to carbon. But the sun is actually quite a puny star compared to some in the universe. So this is a star that's maybe 10 or 20 times heavier than the sun. And you can now see that the Earth is this tiny little dot. And in these very large stars, they kind of live fast and die young. If they're 10 times bigger, they only live for 1/1000th of the time as the sun. And in their cores, you can actually convert hydrogen not just to helium, but all the way up to iron. And when the iron core gets to a certain diameter, it collapses under its own gravity, and you end up with the neutron star being born. And so my job as an honours student was to sort of understand how these neutron stars are born, how much mass is ejected, and whether or not the orbit is disrupted or not due to the explosions. So if we want to think about the evolution of gravity and how it came about, Jupiter actually was the first person to use, Galileo, that was embarrassing, was the first person to use a telescope to look at Jupiter. And when he did, he saw that it had moons and that those moons changed their positions every night. And he realized that the Earth was not a special place in the universe. It was no different than Jupiter. We both had moons. Maybe it was the sun that was actually the center of the solar system. Kepler, on the other hand, was the first person to use the laws of mathematics to describe the trajectories of the planets around the sun. And he stated that they moved in ellipses, elliptical orbits, and that they traveled faster at what we call perihelion than aphelion. And this is Kepler's third laws came about because of that. Einstein showed that Kepler's laws were nothing but the product of calculus and the law of gravitation and his laws of motion, and that you could basically describe Kepler's laws just using his law of gravitation. And I think it's particularly interesting that Einstein did a lot of his best work during a pandemic. He was actually sent home for 2 years, and he developed integral and differential calculus and also the universal law of gravitation. So pandemics aren't all bad, young people, and came back and became probably the most famous physicist until Einstein. And then Einstein realized that there were limitations to Newton's laws of motion, and he showed that any two objects in the universe who were locked in orbit should actually be radiating these mysterious waves of gravity, which required energy to be generated, and that those stars their orbit should shrink. But when Einstein was alive, unfortunately we didn't know about neutron stars or black holes, and so he thought there was no observational consequence for any of his laws of gravitation. So if we go back to our binary pulsar, this is a kind of animator's rendition of how the orbits work. These stars were travelling around each other every 7 3/4 hours, and I used to be able to memorise to many decimal places their parameters. Well, I'm not sure I still have it in my head. And because gravity only travels at the speed of light, their elliptical paths don't actually stay in the same place. They actually precess slowly, and every year the angle of periastron, or the argument of perihelion, I think they call it, actually advances by 4.2 degrees a year. And that's related to how heavy the stars are. And so Taylor managed to use the rate at which this orbit was changing shape on the sky to weigh how heavy the stars were. And then you could use Einstein's equations to work out how rapidly the orbit should shrink, and then went away and measured it. And this was actually the impetus to build gravitational wave detectors. He verified that Einstein's theory was correct, gravitational waves existed, and they should be detectable. So I worked on binary evolution for much of my PhD. If you had a big star and a little star, the big star eventually ends its life and swells up, and it actually transfers matter onto its companion, and you get a role reversal. So the bigger star becomes the smaller star. But it's exhausted its hydrogen in the core, it burns through its other elements, and eventually it blows up. And when it does blow up, you get left with a neutron star spinning very rapidly, maybe 20 or 30 times a second, with a very high magnetic field, and in these beautiful elliptical orbits. And depending on how you observe these things, if you observe them in a configuration where the system is edge-on, you can get an eclipse as the neutron star goes behind its companion. But more often, it's slightly face-on. And you can see the neutron star for most of the orbit. If the neutron star gets too close to the stellar wind of the companion star, it can be lost it can be eclipsed. So my PhD was really about how these systems form and whether the neutron star got a kick or not when it was born, whether these systems disrupted. And I was really just having a good time and enjoying writing down my theories. Eventually, the companion star loses all of its remaining fuel in the core, and it actually swells up, and the material on the outside of the star would rather fall onto the neutron star than stay bound to the star. And so when this occurs, you get this ripping off of material from the giant to the neutron star, and it forms something called an accretion disk. And the accretion disk has its own sort of Keplerian orbit around the neutron star. The material rubs against itself, bounces around a bit. That radiates X-rays because it's so hot. So if you grab an X-ray telescope and stick it above our atmosphere and look out at our galaxy, you see all of these things ripping matter off their companions. And as the material spirals towards the neutron star, it goes faster and faster and gets hotter and hotter. And that's sort of clumsily depicted here by the accretion disk being slightly bluer near the center than it is in the outside. It's sort of redder. And then eventually the material has lost so much energy it can actually fall onto the neutron star surface. And in fact, these things accrete matter at such a rate that the energy density at the surface of them is equivalent to 100,000 nuclear wars per second per meter squared. So if you're falling onto a neutron star, you give off almost as much energy as kind of mc squared. And so these things are remarkably efficient ways of transmitting information across the galaxy in the form of X-rays. The other thing that occurs is that material, as it's falling near the neutron star, actually causes the magnetic field strength of the neutron star to die a little bit. And that was one of the postulates in my PhD. And it also makes the neutron star spin very rapidly. And depending on how heavy your companion star is, paradoxically, the lighter it is, the longer this mass transfer phase lasts. So if you have a light companion, you can end up spinning at 1 kilohertz, so 1,000 times a second, and you can create a millisecond pulsar. If you've got a very heavy companion, the mass transfer phase doesn't last very long, and you can only spin maybe 20 times a second. So all good things come to an end, and this mass transfer phase stops. If you've got a very light star, you're just left with a sort of a rather boring star called a white dwarf and a very circular orbit and what's called a millisecond pulsar. If you've got a heavy companion, you can actually blow up and leave behind another neutron star. And so just before the explosion, you've got quite a tight orbit. It might only be an hour or so. So you have this beautiful pulse radiating through the heavens. We might just see that a little bit edge on. You've got your circular orbit. And then when the other star blows up, you end up with 2 neutron stars going around each other. And this is what was handed to me for my honours thesis to explain. How do you get these neutron stars going around each other? And what sort of experiments can you do with them? So I thought this was fun, and I would have I would get paid to do this one day and become a postdoc. And so I was very keen to get a job. And when I was a PhD student, I sort of self-funded myself to go to a Pulsar conference with the sort of support of my supervisor, Dick Manchester. And I got to meet all of the famous players in this field. And I realised that if you didn't know anybody and they didn't know you, it was harder to get your message out. So I kind of scrimped and scaved to get to China, where the first scientific meeting in China on astronomy was being held. And it taught me that even if you don't have a lot of money, you can get it just by appealing to people. So I wrote to the organiser of the conference and explained to him that I didn't have any money. He gave me $500. It was US, so it was pretty good. Dick Manchester, is this being recorded? At CSIRO, managed to do some creative accounting with my travel grant that I had to travel to CSIRO, and that gave me a bit of extra money. You could claim scientific trips as a tax deduction, because we used to pay tax as PhD students back then, so I got some money back that way. And I ended up meeting, future Nobel laureates and so on at this conference in China. And I was kind of very in their face, I guess. And I met the son of Raman, who was a director of an institute in India, and his name was Radhakrishnan. And he and I had conflicting theories about how pulsars were born and behaved. He thought they didn't get any asymmetric kicks when they were born, and I thought they did. And I wanted to convince him that I was right. And I came up to him at the conference and I went, "Oh, I'm Matthew Bales. I'm so pleased to meet you, Rad. I'm really interested to talk to you about pulsars." And he said to me, "A lot of people think they know a lot about this subject, but they don't." And he said, "Let me give you an example." I thought, this is a bit weird. And he said, if I have a 4.2 solar mass star orbiting a 1.4 solar mass star, and the 4.2 solar mass star loses half of its mass, the two stars fly apart. And I said, yeah. And he said, what is the angle between their velocity vectors at infinity? And I had no idea. And I tried to convince him of my genius and kind of got it a bit wrong, and he sort of talked me through it and explained it. Eventually we got there, and the angle is actually zero. One's chasing the other, which is quite unintuitive. And even though I couldn't answer his question, he did actually agree to talk to me. And we used to have sort of big arguments about who was right and who was wrong. And so when I submitted my PhD thesis arguing for the fact that neutron stars got velocity kicks and he thought they didn't, my supervisor, Ken Freeman, who went on to win the Prime Minister's Prize for Science, said, you should give this thesis to the most influential people in your field, not just choose people who you think will give it a soft mark. So who will give it a good going over? So I said, well, Rad sort of always argues with me. So we gave it to him. And we also gave it to Joe Taylor, who was about to win the Nobel Prize but hadn't yet. And the director of the Dutch Anton Pannekoek Institute, Van den Heuvel, who was actually the father of how these binaries evolved. And I thought, I was really wanting just to sort of annoy Rad by forcing him to mark my thesis and read all my arguments. And he actually marked it and gave it incredibly complimentary comments and recommended me for something called the Crawford Medal, which is what's given to ANU's sort of top science PhD every year. And I ended up winning that award, which was sort of opened other doors for me. So it is worth not just taking the soft option and getting people to read your stuff. So eventually these two neutron stars have given off so much gravitational waves that they end up smashing into each other, and that gives off a burst of gravitational radiation. So my PhD was at ANU, as I've said. I used both the Parkes telescope and the Tidbin-Biller telescope. And this was a brand new interferometer that NASA had paid for. They built a microwave link over 300 kilometres to transmit the data between them so you can combine them into a very big telescope with high resolution. And that's a shot of me living in House 2 on the freezing Mount Stromlo. We didn't have a lot of money. And Chris Flynn's actually here today. As, used to be my running mate when we were PhD students together. So this is the Parkes telescope. It's 64 metres across. It was the only sort of decent-sized radio telescope in the southern hemisphere. And you could kind of control the southern hemisphere's neutron star population by getting time on this telescope. And having access to these sort of national facilities has actually been fantastic for astronomy. And it's one of the reasons why astronomy does so well in Australia. It's because we have investment in infrastructure. And I got to use this telescope for my PhD. My kind of leading contribution, I guess, for how neutron stars observed can be represented on this diagram. This is the magnetic field strength across 5 orders of magnitude, and this is how fast they spin over what used to be 4 orders of magnitude, but we keep finding slower and slower pulsars these days. So the idea was that neutron stars were born spinning very rapidly. They soon are only spinning once a second, because they've given off a whole lot of what's called magnetic dipole radiation. If you grab a magnet and spin it, it doesn't actually enjoy it. It actually gives off something called magnetic dipole radiation. If you do it with a fridge magnet, you can't tell. If you grab a magnet that's 10 to the 12 Gauss instead of 100 Gauss like your fridge magnet, it screams and gives off all this radiation. Makes them slow down and die after a few million years. But if they have this companion, they can get more and more angular momentum back and go faster and faster until they end up in this sort of millisecond pulsar land. So this was my kind of career trajectory. We had a colleague who'd been visiting us after the Challenger mission exploded from NASA, and he gave me a job at Goddard Space Flight Center, which was a lot of fun. We didn't stay there very long because I had another contract at Jodrell Bank. The guy who employed me was a guy called Andrew Lyon. He was one of the most cited astronomers or scientists in England, actually. And I met him when he was visiting my supervisor. They used to write a lot of papers together. And I remember I was starting on my PhD and trying to impress people. And they gave me a circuit board to work on as my first project. And Dick said, oh, that'll keep you busy for a week. So I thought, I'll show him, and I thought I'll stay up till midnight and I'll wire this board. I got to midnight and I was kind of about halfway through, and I thought, you know what, if I stayed up to 1 a.m, I could get even more done. And then eventually at about 7:30, I finished it in the morning, and I handed it to him and I said, there, now what? And people thought, oh, wow, this guy works hard and so on. It turns out wiring a board at 7 a.m. after being awake or not is not a great idea. And I had to sort of debug it. So it probably wasn't a great idea, but it did raise with them the fact that I was ambitious and kind of keen. When I met Andrew, he was explaining to me how interferometry worked. And he showed me a diagram. He said, this is the Nyquist frequency. And I put up my hand, because I'm very honest, and I said, can I ask a naive question? And my supervisor turned to me and he said, you do all the time. And I thought, oh God, I'm trying to impress Andrew here. And they explained to me what it was. It's 1 over twice the sampling time. I know that now. But Andrew obviously didn't hold it against me, and he offered me a job just by me sending him an email, which was great. While I was over there, I learnt about the English Old Boy Network. And there was a guy called Francis Graham Smith, who was the Astronomer Royal, and he was plugged into the Royal Society, and it had these special Endeavour Fellowships on offer, which were a 2-year Royal Society postdoctoral position, followed by 2 years back in Australia with the ARC. And they said the secret to getting these, and this is where I started learning grantsmanship, was not to apply to Oxford and Cambridge, because they get sick of sending them all to Oxford or Cambridge. If you apply to Manchester, you'll get it. And so I did, and became what was called an Endeavour Fellow. and got to go to visit the Royal Society and saw where Newton had signed as a fellow of the Royal Society, and Darwin. And in fact, where Darwin is, so many people have pointed to it that the book is actually soiled by the oil from people's fingers. And I said to the very, I don't know how you, sort of, a gentleman who was showing us this, I said, where do we sign? You're not a fellow. You're an Endeavour Fellow. This is your book. And they brought out a book for us. And then paradoxically, since the Queen had been visiting 30 years earlier, obviously I got the inside running on what's called a Qe2 Fellowship. This is something the ARC used to fund a long time ago. And this was a 5-year postdoctoral position. And what that taught me was if you have 5 years, you can actually put down serious plans and invest in long-term projects. And so I decided I was going to be the best person at timing pulsars, and worked with a guy called Sri Kulkarni from Caltech. And he taught me that you didn't have to do things the way your supervisor did them. And there was this magic thing called digital, and you didn't have to do things in the analog domain. So I worked with Kulkarni on digital instrumentation for the Parkes telescope. And then I realized that Sri's thinking was actually a bit out of date, and you could use supercomputers instead of field programmable gate arrays and do things a lot more quickly. And one of the things our group's been very good at is taking supercomputing and using it for radio astronomy. And nowadays we're designing the supercomputers that will be used to process data from the Square Kilometre Array, which is a $1 billion facility. So I went to Melbourne Uni thinking I'll get out of the CSIRO and stop being my supervisor's student. Was there for a couple of years, and my plan was to get the next fellowship in the ARC's sort of hierarchy, the Senior Research Fellowship. So I applied for that, and about 6 months before the announcements, Dale Murphy actually contacted me, and Dale's in the audience here. It's lovely to see you, Dale. Dale was the head of Biophysics and Electrical Engineering, I think it was called, the school, and said, why don't you move to Swinburne? And I thought, what's Swinburne? I'd seen their signs on trams, I didn't really know what it was. It was quite a new university, maybe 5 years old. And I said, oh no, I'm going to go to fellowship and it'll be fine. And one of the female postdocs at Melbourne was Margaret Mazzolini, and she was quite entrepreneurial and sort of would prod me every now and then, go, oh, maybe you should go to Swinburne, because I think she was working part-time for Dale at the time. So I thought, it was in the back of my head, but I thought, well, I'm going to get my fellowship and just continue doing research all the time. And I was fortunate enough to have a supervisor who was very good at getting papers into Nature. So we used our interferometer to measure the first reliable pulsar parallax, and this helped establish the distance scale for neutron stars. When I was in England, I started learning how to do pulsar searching, and we discovered a whole swarm of pulsars in this globular cluster. Globular clusters are systems of about 1 million stars, and in the cores, all the neutron stars sink down, and they can capture stars and accrete matter and become millisecond pulsars. So I wrote this Nature paper, which was great, and I thought, oh, this Nature paper thing is really easy. And then the next week, I was on the cover of Nature because I'd published a paper about a planet orbiting a neutron star about every 6 months. And this sort of shot me to international superstardom, and I was getting flown around the world to give a talk about discovering the first pulsar outside the solar system. And I thought this was commensurate with my talents, but it wasn't commensurate with a careful scientist checking of the facts. And you might notice I got another Nature paper out of this. In fact, when you do my Nature paper count, luckily one doesn't count as a negative. They both count as Nature papers. But we discovered a software error. It wasn't really a computer error. It was two packages that didn't really talk to each other very well. And the poor student that we'd put on this project and discovered the planet was a little bit mortified. I was pretty mortified too. I think I even cried once. it was kind of grim, and I thought, oh, maybe I should give up on this scientific career because it's not really working out. And then kind of very luckily, somebody discovered a real planet going around a pulsar the next week, or the week before we retracted ours. So I don't know if they were very happy because they were supposed to get international fanfare, and we'd had it for 6 months and then retracted it. But theirs were actually real. And ironically, we actually had a telescope that could have detected theirs, but we were so busy doing our own with our own software glitch that we didn't. So I kind of did a bit of soul searching and thought, well, maybe I should just give up on astronomy. But I thought if I do that, I'll be admitting defeat, and all that part of my career will have just been end in failure. So I thought I'll stick around until I can redeem myself. And we had a lot of really good data coming in. Andrew Lyon had his own personal 76-metre telescope in England, and we really put out a lot of Nature papers in a very short time. So this one discovered that magnetic fields didn't decay unless you accreted matter, which was very exciting. This was a very bright nearby millisecond pulsar that we still observe to this day, and my postdoc was really about enabling this from all the software I produced. And then my first student, his first paper was a Nature paper, which was detecting the optical companion of this millisecond pulsar and proving the theory that it had accreted matter from a companion star. So things started looking up again. And Simon Johnston, who's the sort of godfather of one of my children, and I put together this paper on a neutron star that was going around a very massive star, and this was the first one of these that had been discovered. And then with Vicky Caspi, who's now a very famous scientist in Canada, we discovered that you could actually prove that these neutron stars had received kicks because of the way that this orbit was evolving. So I had all these Nature papers, and then I had a little bit of a setback when I'd applied to be a senior fellow, and in those days you used to actually get your scores for how well you were doing, and you get a number out of 100, and I'd got, everything was above 90 and not a single negative comment. And I thought, well, this is easy. I'll get my 5-year fellowship, and that'll be the next stage of the career. And then I went away to the 30th anniversary Pulsar meeting in Japan and met Jocelyn Bell, who'd discovered pulsars, and I came back and they said, I've got bad news, you didn't get a fellowship. You're in the top 10% of failures. And I thought, yeah, well, that's a bit of a snag. And I said, Dale, I think I might have spoken a little bit too soon. Maybe we should talk again about Swinburne. So Dale took me to some cheap Malaysian place on Burwood Road, and we had a chat, and he showed me around where I might be able to sit. And I remember looking up, and it was in this horrible green building that used to be on Burwood Road, and it had a skull and crossbones on the roof, and it said, "Danger asbestos." I thought, oh, this isn't so good. But then I had actually, although I'd failed to get this grant, I had got a discovery grant as well. So I had 2 discovery grants that were active. And, you know, I'd hoped to have my own salary as well, but that hadn't worked out. And Dale had worked out if I brought 2 grants over here, that would help Swinburne's performance. I didn't realise at the time, but I think Swinburne only had 6 grants in the entire university. So bringing over another 2 was like a big percentage increase. And kind of had a bit of a to and fro with Melbourne Uni, and all of a sudden they got interested in keeping me and offered me a job. But I rang up Dale, and Dale said, why don't you just think of some crazy demands and try us? And I thought, okay, make me a level D, give me my own supercomputer, get scholarships for all my students, and I'm yours. And he said, let me talk to Ian Wallace. And this was in the days when you could have a hotline to the VC. They weren't surrounded in protection. And 15 minutes later, the phone rang, and Dale said, anything else? And I thought, well, that's a pretty good deal. So I talked to my head of school at Melbourne, and he said, this will be a huge mistake if you go to Swinburne, and I thought, well, it's a bit like a 5-year kind of postdoc, bit of fun. And I think Dale said to me something which really changed my mind, and he said, at Swinburne you can do anything. And I thought, well, that flexibility sounds good, because I mean, Melbourne Uni doesn't have to do anything. They've got a really set way they do things. It works for them. They get good students, they get lots of money. Their VC earns $1 million a year. I mean, it's all kind of working for them. Why should they change? But at Swinburne, we had to be radical. And I really enjoyed Dale's, the way he painted this sort of blank canvas that I could do anything on. So I thought, yeah, I'll come here. And so I met Ian Wallace, who was the VC back then, and Margaret Mazzolini was also quite clever in her ideas and a very hard worker. And she was almost like my sort of deputy director when I first came here. And I felt a bit weak having something called the Centre for Astrophysics and Supercomputing with 1.4 FTE in it. But I had enough money for a postdoc, and we had students, and it was quite an exciting time. Then I got to mix with cardboard king billionaires and so on. And Dale supported me, but unfortunately Ian Wallace almost had too much faith in the people he had appointed. So he had this great belief that he must have appointed some sort of genius, and he would say things like this, and I'll just let you read it. I think it was a little bit of an exaggeration. And I particularly like the last bit. I only found this last night when I was Googling Ian Wallace, Matthew Bales, and this is what comes up. And it has this: Matthew was receiving an international offer about once a week. It's not quite how I remember it. I certainly had the odd inquiry from overseas, I don't know, offers, but anyway, he did manage to keep me, which was good. And I mean, I think Ian was also interested in kind of radical ideas and doing things that were different. And he wasn't afraid to make some tough decisions to give people like me money to do stuff, and it worked out. So we built 16 DEC alpha computers in an abandoned office, and we actually got 2 exhaust fans as the heating control system, punched holes in the roof and just used to pump the hot air out. And supercomputing, I think, has really been something that's worked very well for Swinburne. It is the University of Technology, and I think we've now had 7. Jared now manages it for me, and we got $5 million this year from the Victorian state government to replace the current OzStar machine. And it's exciting, the sort of science this has enabled us to achieve. So the centre was created, and Dale had this idea that we should get into online education, and that worked really well. But a few months into planning this online education, I'd actually written to the ARC expressing how disappointed I was with the whole system and how you could get these scores above 90 and still not get a fellowship, even though you didn't have a single negative comment. And I was just going to send it off as a rant. But there was a very clever lady at the Melbourne research office and said, actually, you're not allowed to just write to the ARC randomly. You have to go through a formal process. And why don't we make it an appeal? And then they'll have to review you. And that's a better way of raising these issues with them. Because you're not going to get the grant anyway. You're just going to make yourself feel good by ranting at somebody. So we appealed, and then they re-added up my numbers, and they realised that they'd forgotten to multiply by, there was a bonus factor if you're an existing Qe2 fellow. You got like a bonus factor. And if I'd got that bonus factor, I would have got my fellowship. So I wouldn't have come here at all. So we actually have the ARC to thank for all that. So I rang the ARC and said, oh, look, I'll take the fellowship, but I want to move it to Swinburne, not Melbourne Uni. And the head of the appeals tribunal, who actually went on to be a VC, said, Swinburne will never get a senior fellowship because you've got a terrible reputation. The only reason you've got this fellowship is because you put down Melbourne Uni is where you would host it. Otherwise, you wouldn't have got it. And it was the only time in my professional career I lost my temper. I started yelling at this guy over in my office. And I thought, oh, maybe that wasn't such a good idea. And so Ian Wallace organised an official trip to Canberra with what was then the Pro Vice-Chancellor of Research, and the head of the ARC, Vicky Sara, overturned the tribunal or the appeals committee, and I was allowed to keep my scholarship here, or take my fellowship here. And Ian Wallace sort of welcomed me into his office, and he already had this great overblown view of me, but it was the first time Swinburne had got one of these things. And he said, "You don't seem that happy about it." And I said, "Well, actually, it doesn't really change my life much. I'm still getting paid, you know." And he said, "Oh, nonsense. I'll cut you a cheque for how much salary you've saved me, and I'll create an account and you can spend it on whatever you like." And so I thought, "Oh, that's pretty good." So I got sort of $500,000 spending money, and we set up this online venture in astronomy, which ended up being very successful. And one of the things that made this so successful was we weren't getting many students, and we needed to advertise. And Margaret had this clever idea that if we could put a CD-ROM of the content on the cover of every Sky and Telescope magazine, that would be the best way to advertise the course. And so I went to Ian Wallace and I said, "Hey, we've had this great idea. We're going to put a CD-ROM on the cover of every magazine. The only problem is it's going to cost $250,000, and this is $1999. And he said, "Well, write me a business case." And so I went away and invented some numbers and showed him the business case. And he said, "Oh, sure, let's do it." So we did it. And within like a year or two, we were getting $500,000 a year back from this course. And it enabled us to really expand how many people were in the sort of astronomy department that was rapidly growing. So we recruited Duncan Forbes and Brad Gibson, and Margaret's time fraction went up. We also got Sarah Madison, who's now in the hierarchy here, and she was a real dynamo. Chris Fluke came over to do what I called commercial work at the time. But we also got people like Warwick Couch and many more. And so this was a really exciting time. We were doing kind of new things. We started working on virtual reality. But for Ian Wallace, this wasn't good enough. He wanted a faster pace. And so he said, he invited his 6 kind of like prophets in. So there was sort of what he called the parachute professors. And he said, "Give me one A4 page of justification and one budget, and I'm going to fund more expansion for you." So we did that, and I actually found it last night. So this was all I needed to do to get almost $2,099,000, I think it was. And I explained what we were going to do. I love this. We were going to buy a 1 terabyte mass storage device. And the 1 terabyte disk array was going to cost $90,000. So this is what you needed to spend to get that sort of storage. But this was going to transform us into a Pulsar superpower. And so we ended up funding all our sort of priority A things. And I realised that the way to get money out of people was to pretend you were earning a whole lot elsewhere. And so this was, our online education and various other things. And then one day the head of finance rang me up and said, "Okay, I'm ready for my $250,000 back." I didn't realise it was a loan. So I rang up Ian Wallace and I said, "I don't actually have the $250,000, I've already spent it." He said, "Let me talk to him." So luckily we produced Swinburne's first Nature paper, which started sort of improving our rankings. And this was by my great student Willem, who'd come from Canada to work for me. And we had a mascot, PSR Wombat. PSR Wombat used to drive to the Parkes telescope. He used to visit tourist attractions. He used to announce the clear call that the dish was about to move. He used to take the odd break, climb up the telescope to change the feeds and sort of admire the sunset. But we had a great spirit in the centre, which I really enjoyed. How much longer do I have, Enzo? Not long, I guess.
You owe me 10 minutes.
Oh, really? Okay, so Ian Young was very supportive, told me that I wasn't getting as much money as the other Tier 1 centres, and what could I do if I got more people? So we hired a bunch of other astronomers. We did some great things in virtual reality, which I'm very proud of, particularly with people like Russell Scott and Chris Fluke. Made our IMAX films. We even put in virtual reality theatres in places like Thailand. John Brumby came and gave us money for the original VR theatre. And we had lots of little kids come in over the years to get educated about astronomy. So I'm just going to buzz through, since I'm already behind time. We've done some great experiments with these millisecond pulsars and how space-time is bent. We discovered one pulsar eventually with a planet that was real. So this was the so-called diamond planet. This was another science paper for Swinburne. And in fact, we started writing so many science and nature papers in the wider centre that we did get the university into the top 500. This is a particularly interesting object that is influential on gravitational wave discovery from supermassive black holes. Its orbit is so circular that the difference between the semi-major axis and the semi-minor axis is only 3.7 microns, even though the orbit is about 1 million kilometres in diameter. We keep finding pulsars with the generously provided Swinburne supercomputers. And one of my former students, Duncan Lorama, in fact he was my first student, worked with his summer student, and they discovered this thing called the Lorama Burst, and this was the first fast radio burst. The first fast radio burst was actually visualised by Duncan and I sitting in the park's control room, and when we saw it, we just noticed how similar it was to pulsars. But we didn't realise that it was coming from halfway across the universe. And so just like the quasar that was discovered on the day of my birth with this ridiculous luminosity, these fast radio bursts are so dispersed because of the finite speed of light going through past electrons that it's actually travelled over 3 billion light years. And so this was an unplanned for thing, but it came about because we'd invested in infrastructure developed here at Swinburne over many years. And the luminosity of the Lorama Burst in green was something like 12 orders of magnitude greater than anything known at the time. And now we've filled in this whole phase space, and it's been a very exciting journey. I was particularly proud of this discovery where we discovered the population of fast radio bursts, and this science paper with Swinburne on it has, I think it's 800 citations, and the Lorama Burst discovery has over 1,000 now. So I'm not going to go through all of this or how the models of fast radio bursts work because I don't have time, but I think it's very telling that now my former students and postdocs are doing great work in this area and actually measuring the total mass of the universe using fast radio bursts. And this will be a very famous and very well cited Swinburne Nature paper as well. So let me just walk to the finish line. We had the great alien thing where a Russian billionaire wanted somebody to help him find aliens, and we sort of did some work in that. We made a commercial for Lexus that landed the university $50,000 for one day's filming, which is kind of fun. These days, Ryan here is leading some of the searches for gravitational waves from supermassive black holes instead of just black holes, sort of solar mass black holes. I was brought in to unify the warring tribes in Australia to lead the Centre of Excellence for Gravitational Wave Discovery, and that's been a tremendous thing to actually see black holes merge and make the very fabric of space-time shimmer. And be able to detect that using these sort of $500 million facilities in the US called LIGO. So we've actually seen not only black holes merge with LIGO, but neutron stars. And in fact, the very paper that I was given in 1984 with the 2 neutron stars, we saw an example of that system coalescing some 300 million years later in the form of a neutron star merger. So these 2 neutron stars, eventually give off so many gravitational waves that they coalesce and they give off a burst of light. And with LIGO, we could not only locate where in the sky that was, but look through all of the galaxies in the 60F galaxy redshift catalogue and identify the galaxy that hosted the neutron star and see the new star in the sky. So I've been very proud to have been both in charge of all the astronomers at Swinburne, but also in charge of the National Centre. I'd like to thank Swinburne for the opportunity to do that, and also to the wider community for being so supportive of astronomy here, and particularly Dale for coming in today. Thank you, Dale. All right, back to you, Enzo.
That was amazing. I thought at the early part of the talk when you mentioned, was it Greyburn Road?
Glenburn Road.
Glenburn. You've gone from Glenburn to Swinburne. So, and you must be an expert in crossing Burwood Road when you're in the traffic. Let's have some questions. I know we've got refreshments waiting, but I think we can't let Matthew go without some questions. So everybody wants to ask any questions? Paul's going to have the roving mic. Everyone's too shy. No.
Who ended up being right about the debate about pulsar kicks?
Yeah, so the question was who ended up being debated about the right of pulsar kicks. Yeah, so it's quite fun actually. Radhakrishnan was an extremely interesting and extroverted figure, and he's actually passed away now. He would be well over 80, I think. He used to smoke and drink lots of whiskey and so on. I think it's true that neutron stars often do get kicks, but recently, ironically, one of my students found a system where there was no kick. So it turns out that if you're too close to your companion star, you can lose so much material in what's called an ultra-stripped supernova that when you blow up, you get no kick at all. And so we published a paper this year on that the system has no kick. So it's kind of funny that if that had been the first one discovered, we might have thought RAD was right. But we've discovered these other examples where neutron stars are going 1,000 kilometres a second, and they obviously did get kicks. So you can both be right. And I actually became very good friends with Rad and visited him in India, and his wife sort of helped cure my Delhi belly by giving me special home brews.
Any other takers? Yep. Front. Thanks, Jen.
Matthew, thanks so much. That was just wonderful. You describe work that is so big and so sophisticated, but at the same time, you convey a sense that it's almost like just kind of simple curiosity. So I guess I wonder if, when you look back, when you're advising your students, when you're talking to postdocs, is there anything that you really try to convey to them about scientific curiosity, not making things feel or seem more difficult than maybe they need to be?
I think, I used to think I was pretty good at maths, but I went to university and met some people who were just like wizards and had a real natural talent. And I certainly know there's areas of science that are off limits to me, just because I don't have the brain power to do them, like differential geometry. I really like the sound of being a theoretical gravitational theorist, but I didn't actually have the mathematical capabilities. But I think what I do tell them is that there's actually still lots of easy bits of science to do if you just think about it. So I think there's like a lot of easy things to do. And I think a lot of the stuff we do is actually based on a few equations that are quite easy to understand. And just not wasting your time trying to do things that you don't have any natural talent in is what I tell them. So, I get a student, you'd be good you're a careful student, you can look through things carefully, or gee, you're really gifted mathematically, or you can cut code. I usually think there's an area of science they can usually contribute to. But it doesn't, just because they don't understand everything, it doesn't mean they can't be a contributor to some of it.
Hi, Matthew. Thanks for your talk. I have a question, but I'm not sure whether it's directly related. But so is space-time real, or is it just in our perception?
Well, I think space-time is beautifully described by Einstein's theories, and so to that extent it's real. Whether or not this whole universe is just a theory, part of my imagination, I can't actually tell you. But it certainly seems that when we do these experiments on these naturally occurring laboratories, the Einsteinian description of how objects should move does seem to be very accurate. So I suspect it's real, and I hope all of you are real too. Good.
Hi, thank you so much. Lovely talk. You've talked a lot about sort of the past and how you've come to be where you are now. I was sort of wondering, what is your envision for the future? What's next?
I'm glad you asked that, because I'm just coming to the slides on that. So we've done a few things. We've taken some of the technology that we've used to study the stars, and in particular capture data from radio telescopes, and we're now applying it to satellite communication. So we've created a spin-off company, Space. Virginia and Ian Young are on the board of that, and a bunch of former students and postdocs either work on it or are part owners. We're working on something called the Square Kilometre Array, which will be a $1 billion facility coming online by the end of the decade. And we're also working on making the current LIGO gravitational wave detectors, and I didn't really go into these very much because it wasn't really part of Swinburne when I started, but these are these vacuum tubes in America that are 4 kilometres long, 2 arms at right angles, and they actually detect these gravitational waves as they pass through them by measuring the difference between the mirror, the spacing between the mirror and the laser beam to an accuracy of about 1/10,000th of the width of a proton. And we keep making them better and better, and OzGRav is contributing to the improved performance. And they have these observing runs, and these are the range of the observing runs, and we're about to enter 04, which is being delayed by COVID, but it'll start by the end of this year. So we being able to see like double the distance. If you can see twice as far, your event rate goes up by a factor of 8. And the target is to eventually get these out here and then build what's called the 3rd generation detectors. So there's already a science case for building detectors that instead of having 4 kilometre arms will have 40 kilometre arms. And they'll be able to detect gravitational waves from the entire universe. So this is a vision that we've given to the Australian Research Council, and we're applying for something called the 2nd edition of OzGRav, which is our Centre of Excellence. And we're having the interviews for that in August, don't forget, Karen. And hoping to get another $35 million with the headquarters here at Swinburne to do gravitational wave science, not just in this decade, but maybe for another 20 or 30 years.
Brilliant. Thank you.
If I may just indulge and ask a question from the chair. In these days of funding bodies asking about the commercial outputs of research, a lot of your research has come from fundamental science. You probably had no idea what you were really going to do with the knowledge that you've received over this time. What's your response to this idea that everything has to be commercial and applied and has a sort of a business case and so on around our research?
Yeah, I think my view is that if you're spending $100 billion on submarines because somebody might attack you one day, or somebody you've annoyed might attack you, that's pretty sad. And I think humans have a responsibility to try and increase knowledge. And a lot of the things that we have done, they don't have any immediate commercial application. I think one thing I find discouraging about many areas of academia is that they they talk about industry as if it's a dirty word or some sort of lesser use of your time. And I don't view that at all. And we've always tried to do commercial work. I think Chris Fluke is probably in here somewhere. He was hired to do commercial work with CAS, partly because I just wanted another alternative funding stream and discretionary cash. And I certainly don't think of industry as a dirty word or in any way lesser than what I'm doing. I think I'm probably better off doing science than working commercially. But we've tried to, in OzGRav, encourage an entrepreneurial, encourage people to think about entrepreneurship and the fact that they might leave academia. Because if I supervise 30 PhD students, they all can't become Matthew Baleses. Otherwise, we'd have an exponential growth, and that would be, nobody would want that. So probably 29 out of 30 will leave, won't follow in my footsteps. So I've always encouraged them to think about doing entrepreneurial things. And we had a lovely example earlier this year where 2 of the ANU students created their own company, and they ended up selling it for a very large figure to another company. And they were just using laser beams to do gravitational waves, but they ended up applying it to LiDAR for autonomous vehicle navigation. So, that was a happy ending for them.
Okay, well, I think we have some refreshments waiting for us in the Sky Lounge, but before we adjourn, I'd like to ask you to join me in thanking Matthew for an excellent presentation, and also from somebody who's been around during much of that journey for really making astronomy and Swinburne being put on the map through Matthew's activities and his many colleagues. And again, it's a fantastic recognition of his work as now a Fellow of the Australian Academy of Science. So thank you, Matthew, and all the best for the future.